We left you with this question about how you would determine the distance x over z to the point or points where the anomaly falls off to 3/4, 1/2, 1/4 of its maximum value. Remember, we did this because for each one of those diagnostic positions, we're able to estimate the depth z from this value of x over z that we get. So we have an expression here for just to confuse you, we're using some different notation here, but these are both vertical anomalies, and we're just saying h sub z, the vertical anomaly, over h max. For the cylinder, 1 minus x squared over z squared, 1 plus x squared over z squared. Well, to make life simple, we're going to let z equal 1, so we're really solving, we want to know when h sub z over h max, in other words, when does the anomaly fall off to 1/2 of h max, when this is equal to 1/2, or when this ratio is equal to 1/2. And so we've simplified our algebra by letting z equal 1, but pause and try to solve these. This is for the cylinder, this is for the sphere. Try to solve for the value of x, or x over z. That's what we're doing, but we're letting z equal 1 to simplify this ratio here. And your algebra skills are probably better than mine, but I decided, well, I'm not going to, I spent a little bit of time on this, but I decided, well, I'm going to use Solver in Excel in order to figure out the value of x over z at these different diagnostic positions. This is the cylinder, the sphere down here. These are the expressions that we just showed over here, so that we're solving for. So let me bring up Excel and just kind of show how Solver works. You would go to Data in your ribbon above, and one of the folders, and if you've gone to File, and I think I can show that. If you go to File, Options, you'll be able to load Solver. But let's see how this works. In other words, when you open up the Solver window, your objective cell, this is the objective cell. The objective cell has the formula in it. This is the formula for R. This is the formula that we want to solve. In particular, we want to solve for the value of x over z. That will give us 0.5, this 0.5 over here. So when does this, we need to solve this equation in order to get a value of 0.5, and we want to drop that number into the cell D3, and then we just click Solve and we're done. So I'll bring up Solver and say that's pretty much how we get this value for the diagnostic position of 0.5. Now if I bring up Solver, I've got the same objective cell location, that's our E3, but let's say instead of 0.5 I want to solve for 0.75. In other words, I want to know what value of x over z the anomaly falls to 0.75 of its maximum value. And so I'll hit the Solve button. I don't know if that's off the screen. There it is, I think. And it will automatically put in this value, the value that you see here. And so I just did that for each one of these diagnostic positions, and in order to get these values of x over z. And then remember, we take the reciprocal of these values in order to get the depth index multipliers when you're dealing with an actual anomaly. you're multiplying the distance at which the anomaly falls off to 3/4 of its maximum value times, let's say, 3.21 in order to get the value of z, the depth to the center. If we do that for all these positions, all the values of z that we estimate should be the same. And you might go back and do a little bit of review, but hopefully this sounds familiar. And let's go back and take a look at some slides. So again, we have these. I put in a 0.9 here. You can put in, basically you don't have to go 3/4, 1/2, 1/3, 1/4. You can put in anything you want, any diagnostic positions you might like, and solve for the value of x over z. In this case, this is for the sphere. This is for the horizontal cylinder. These are the diagnostic positions. Okay, so if we come over here, we do like we did before, the diagnostic positions for the vertically polarized horizontal cylinder. They're listed over here: 3/4, 2/3, 1/2, 1/3, 1/4. These are the values of x over z. These are the depth index multipliers. Now, take a few minutes and determine the depth to the center of the cylinder that produces this anomaly, the anomaly that you see here. So we've got a maximum value of 20. So it will fall off to half of its maximum value at 10. It'll be right in there. So that's going to be about 9.3, 9.44 or so. And I've highlighted these over here. Different anomalies, sorry. But the same idea. We're looking at the positions at which the anomaly drops off to 3/4, 1/2, 1/3 of its maximum value. So I didn't do it for all the diagnostic positions here. I only used 3. We could have used more. If we had more noise in the data, we might have wanted to concentrated our measurements up here. So we may have wanted to choose some different diagnostic positions rather than 3/4. We might have wanted to use 0.9, 0.8, 0.7. So it can be arbitrary. And I've shown you a way to do this with Solver, so you might find it easy to do to get around the algebra that way. And you might decide to do this sort of thing if you do have a higher signal-to-noise ratio. If you do have a good bit of noise in the data, particularly at the lower, tends to obscure the anomaly when you get down into the noise. So here we are for the horizontal cylinder, and we've come up with depth estimates. I added an additional one in here just to illustrate the idea. We were coming up with at 3/4, 1.96, 2, 1.94. Added in at 0.9, we get 2.08. So just taking a look at an average, we'll just call it 2. And so this is just kind of a reminder of what it was that we did with gravity when we were using simple geometrical objects. We were using the depth index multipliers obtained from these different diagnostic positions for each of the anomalies that we looked at. In this case, the horizontal cylinder. These are the values of x over z at which the anomaly falls off: 2.9, 3/4, 2/3, 1/2, and so on. These are the depth index multipliers. You read off a particular value of x, you multiply it by, I think this should be moved over here to about 1/3. That would give you 1.94. So that's all we're doing, is trying to get estimates of z, and then we take averages here in order to get kind of an average estimate. We assume that we don't, even when you have a pure signal like this, you'll come up with some variability, as I did here. Now imagine that you're working with real data, then this noise can be more significant and more of an obstacle to getting so you'll want to use more of a statistical average in order to estimate z. So for the sphere, we do the same sort of thing. I added the 9/10 diagnostic position in here, 3/4, 2/3. And we're just taking a look at, we figured out what the values of x over z, what the depth index multiplier should be, And then we just have to mark off those positions, and I'd leave this for you to do. What is the depth to the center of the sphere producing this 5.4 nanotesla anomaly? So next time we'll consider a problem and we'll kind of put these ideas into practice. If you have questions on this and would like some clarification, I could spend some more time maybe on solver. But hopefully that gave you a good review and refresher of simple geometrical objects and the idea of diagnostic positions and the depth index multipliers as a way to obtain the depths to the center of objects that you think, as an interpreter, and that's a key decision there. You think it might be an anomaly produced by a sphere. If it is a sphere, then all these depths should be about the same. If the depths turn out to be different, then your interpretation is most likely wrong. So anyway, hope you join us next time, and we'll take a look at a couple problems and continue on with the use of simple geometrical objects. See you then.